and was a young investigator fellow at Karlsruhe Institute of Technology, and she just recently started as an assistant professor at the University of Arizona. So today she's going to be talking about two perspectives of ice microphysical impact on cloud radiative heating. So Sylvia, please go ahead.
Thank you. Thank you very much for the nice introduction. You can hear me all right, right?
We can hear you fine and we see your screen fine.
Okay.
So please begin.
Great. Some work that we've been doing over the past few years with you today concerning ice microphysical impact on cloud radiative heating. So I've done this work primarily with Eiko Vogt, who's now at the University of Vienna, but also Annette Miltenberger, who's at the University of Mainz, and Christian Rolf and Martina Kramer at the Research Center in Jülich. So the funding for this work came from the Ministry for Education and Research in Germany, as well as the German Research Foundation. And initially, I was going to share results from two studies that we've now published. But I decided that I would include also results from a third study that's in preparation. So you get kind of a post Black Friday deal today. You get 3 for the price of 1. So with that, let me jump in and give a little bit of background on cloud radiative heating. We often talk about cloud radiative effects in terms of sort of two-dimensional fluxes. So thinking about how clouds alter fluxes either at the top of the atmosphere or at the bottom of the atmosphere at the surface. And so you can see 2 of these kinds of two-dimensional fields of cloud radiative effects from the IPCC assessment report 5 here. So in the short wave on the left and in the long wave on the right. And so at the top of the atmosphere, clouds tend to cool by reflecting ultraviolet or visible radiation. And then in the long wave, clouds tend to heat because they absorb infrared radiation that's been emitted from Earth's surface. But along with these kinds of two-dimensional radiative effects, clouds also have a three-dimensional radiative effect within the atmosphere. And we talk about that three-dimensional radiative effect in terms of a heating rate, a cloud radiative heating. And that's a flux divergence, so how much these two-dimensional fluxes change as a function of altitude or pressure. So you see a qualitative picture of one of these kinds of cloud radiative heating profiles at the bottom. And this is a cloud radiative heating profile that would be associated with ice cloud outflow. So ice clouds generate a radiative heating. I think you can see my mouse, hopefully. Radiative heating and cooling dipole in the atmosphere. So there's an in-cloud heating that has to do with the fact that ice absorbs more infrared radiation than does clear sky. That has to do with an absorption cross-section. So you see that over here on the right. For ice, that absorption cross-section is orders of magnitude larger than for a molecular absorber like gaseous water vapor in the dark orange. And this is an infrared wave number. So ice absorbs more than would clear sky, and then that absorbed infrared is re-emitted out to space, and so that causes a cloud top cooling. So why would we care about predicting this kind of cloud radiative heating? Well, it's because clouds and circulation are coupled, and we can see that in satellite images of clouds. Where clouds form reflects the underlying circulation. And this has become a very active area of research, this kind of coupling between clouds and circulation, because it's not only circulation that determines where clouds are formed, but once those clouds are formed, then they feed back on the circulation via, for example, radiative or latent heating. And so let me give you a variety of ways in which cloud radiative heating in the atmosphere can affect the circulation. It can lead to increases in tropical stability. It can tighten the ascending branch of the Hadley cell. It can push the eddy-driven jets poleward or equatorward. It can intensify El Nino, prolong the North Atlantic oscillation, shift and strengthen the Northern Hemisphere jet stream. So there are a variety of ways in which this coupling occurs, not only in the tropics, but also in the mid-latitudes, not only for large-scale circulation cells, but also for modes of interannual variability. And so if we begin to kind of construct these cloud radiative heating profiles from different sources, what we find is that they vary. So you see that here for tropics-wide mean cloud radiative heating profiles from 3 models in the color, 3 global climate models in the color, relative to a satellite climatology in the black and reanalysis values in the dashed black. And then the same is kind of true, this variability in the mid-latitudes on the right there. So these profiles are not only quantitatively, but also qualitatively different from one another, and that's going to then have implications for circulation. And so we started this work asking how much cloud microphysics contributes to this kind of variability. And because the variability is particularly strong in the upper troposphere, and also because that upper tropospheric variability is what's most important for circulation, we're going to focus primarily on ice microphysics, so cloud ice microphysics. And we're also going to be interested in how much ice microphysics contributes to variability relative to other model settings, like vertical or horizontal resolution, or the convective scheme. So I told you I was going to give you kind of different perspectives on this link of ice microphysics and cloud radiative heating. First perspective has to do with kind of a vertical or thermodynamic axis. So if we think about different processes that are happening in the upper troposphere within these ice clouds, they're a function of temperature, strongly temperature dependent. There's another axis, which is kind of a temporal axis, right? So different processes will happen at different points in the ice cloud life cycle. And then we can sort of conceptualize these processes as existing in sort of regions of this space. So something like nucleation occurs at colder sub-zero temperatures and is more associated with formation of the cloud. Secondary ice production, which is received increasing attention over recent years, happens a little bit later in the life cycle. It requires some primary ice to have formed already, and it also occurs then at warmer sub-zero temperatures. And as the ice cloud develops and those crystals can aggregate, and once they grow big enough, then they can sediment out, and that's kind of associated with dissipation of the ice cloud. So along with this kind of vertical and temporal axis, we might also just think about separating these processes out into kind of a dichotomy of sources and sinks. And there is some ambiguity here, right? Something like aggregation is a sink of ice crystal number, but not necessarily of ice mass. But in general, we can think about sort of source sink processes, and those are then a function of cloud parameters, which are very values that we would assume a priori, like the density of ice crystals, for example, and cloud controlling factors, which would be both thermodynamic and dynamic inputs to the formulations of these different processes. So I want to start with this kind of first perspective, which looks at the thermodynamic axis. And so there's kind of a mathematical formulation of it over here to the right, thinking about how ice mass and number are formed as a function of sources and sinks that are temperature dependent. And so to understand microphysical impact on cloud radiative heating within this framework, we're going to use limited area simulations. And limited area simulations with the icosahedral non-hydrostatic model, or ICON. And we're going to run ICON at 2.5 kilometer equivalent resolution, which is sufficient to explicitly resolve deep convection. We run 3 days of simulation that correspond to the StratoClim flight campaign in August 2017, and we have a 24-second time step. So within this setup, then we're going to kind of flip 4 different switches. And the first switch has to do with how we formulate our microphysics, whether we use a 1-moment or a 2-moment scheme. So I'm going to use this terminology quite a bit, 1 moment and 2 moment. 1 moment means that the model is only tracking the amount of mass, which I'm designating as Q, the amount of mass of ice in the cloud. Whereas the 2-moment scheme is going to track both the amount of mass and how that mass is distributed, so the number of ice crystals. Then the second switch has to do with vertical resolution. So by default, the model has 75 levels, and we'll increase that, particularly in the upper troposphere, to 120 levels. The third switch has to do with aerosol dependence in our nucleation scheme. And the final switch has to do with the size of our crystals, the effective radius, and whether that effective radius is consistent between the microphysics and the radiation schemes. So then what I want to do is build up cloud radiative heating profiles like we talked about earlier from these different simulations. So you see here, we're using pressure here as a vertical axis, and you have the cloud radiative heating along the X. And so I want to start with looking at the reanalysis profile from ERA and a satellite climatology from CloudSat Calypso in the light blue. This is over the simulation domain, over the Asian monsoon region. And so already kind of building profiles from these observational or pseudo-observational products, we have a problem because we don't have a consistent baseline to which we want to compare. Now, if we start to add the simulations in, then in the orange trace here, you see simulations that use the 1 moment microphysics with default vertical resolution in the solid line and with higher vertical resolution in the dashed line. And so that vertical resolution is not having so much impact on our profile. What does have a big impact is switching from a 1 moment to a 2 moment microphysics scheme. And so you can see that kind of heating cooling dipole that I mentioned before is stretched out in the 2 moment scheme. So we get about 2 times as much in-cloud heating and almost 10 times as much cloud top cooling from switching the microphysics scheme. And if we keep going now and look at the simulation that uses a consistent treatment of effective radius in yellow here, then we again stretch that dipole by a factor of 2. If we look at the simulation where we include aerosol dependence in the nucleation scheme, then we moderate the dipole a little bit. And I'll give you one more where we kind of flip all of the switches at the same time in orange. So we have a 2 moment microphysics scheme, aerosol dependence, and a consistent treatment of radius. And if you squint here, amidst all the profiles, and that orange profile is the one that agrees best with the profile from ERA. So the takeaway from this kind of building up of profiles is that we get this spaghetti plot kind of radiative heating profiles, right? We can kind of generate whatever we want with these ice microphysics switches, and that's a little bit disconcerting. We get a factor of 4 difference in that maximum cloud radiative heating between different simulations. But we can also understand why, and that's where this kind of vertical perspective comes in. So to first order, the reason that we stretch that heating cooling dipole in the 2 moment scheme relative to the 1 moment is simply because the 2 moment scheme produces a lot more ice. And you can see that in the vertically integrated sense here, where we're looking at probability distributions of ice water path. So ice water path is just the integrated amount of ice that I have in the cloud. And so in a mean sense, the mean integrated amount of ice is larger in the 2 moment scheme. And we also see this qualitative difference where we get a bimodal distribution in the 2 moment scheme. And the 2 moment scheme produces a lot more ice, not only in the vertically integrated sense, but also over the full depth of the cloud. So from about 500 hectopascal all the way up to 100 hectopascal. In the blue there, you see a lot more ice mass being produced in the 2 moment scheme. And so we can ask why there's so much more ice being generated. At the lowest altitudes, ice is forming via heterogeneous nucleation. So these are somewhat warmer sub-zero temperatures, and ice can form on aerosol particles. But if we look at how that heterogeneous ice nucleation occurs solely as a function of temperature, we can see that it's not very well constrained by in situ measurements. You can see that in the scatter plot from DeMott et al. So if we're only representing this as a function of temperature, then we have quite a bit of uncertainty, for example, in this prefactor A. And that manifests then if we look at the parameter values in the 1 moment scheme in red versus the 2 moment in blue. So that the pre-factor, which we can kind of understand as an efficiency of heterogeneous nucleation, is 2 orders of magnitude larger in one scheme than the other. And that higher efficiency then is going to generate a lot more ice. And we can test that in the purple trace over here on the left by taking the value of A in the 1 moment scheme and putting it into the 2 moment scheme. And when we do that, when we just switch this kind of efficiency factor, then we can get the ice mass profile from the 2 moment scheme to collapse down onto the 1 moment scheme. So once we form initial ice at those lowest altitudes, then we have subsequent processes like aggregation that occur, or ice to snow conversion processes. And what we found is particularly influential is something called ice autoconversion, where 2 ice crystals stick together and then they're converted into the snow category in the microphysics. So if we look at the snow mass mixing ratio, Q sub S, over here on the right, it's a mirror image of the ice one. So we have a lot more snow in the 1 moment scheme in the red than in the 2 moment. And that's because the 1 moment scheme converts ice very efficiently to snow. Just over a fixed time constant, then ice becomes snow in the 1 moment scheme. And in contrast, in the 2 moment scheme, then it's a much more sophisticated representation that you see here at the bottom. It depends on these kinds of delta and theta factors that have to do with the size distribution of crystals in the 2 moment scheme. And so that more sophisticated formulation will convert ice to snow much more slowly. It's important to note too that snow is radiatively inactive in the model. And so if I quickly convert all my ice to snow, then I reduce the radiative heating from clouds significantly. And finally, then at the highest altitudes, ice is forming primarily via homogeneous nucleation. So there's some kind of supercooled droplet. There are molecular fluctuations within that droplet that can form an ice stream. And that ice stream can then grow into a larger ice crystal. And this homogeneous nucleation then is going to be driven by generation of supersaturation, which is kind of vapor excess or excess vapor relative to an equilibrium value. And that's generated then by ascending to colder temperatures and lower pressures. And so we look in this case at profiles of ascent rate. I'm using pressure velocity as our metric of ascent rate here. And so then if you're looking at these difference profiles in that pressure velocity, then what these negative values mean is that in the 2 moment scheme in blue, the ascent rate is much higher, almost 2 times higher in the upper troposphere than in the 1 moment scheme. So if we have a higher ascent rate, then we're going to generate supersaturation more rapidly and promote homogeneous nucleation in the uppermost part of that cloud ice profile. So with that, I'll kind of wrap up this first perspective and say, in these limited area simulations in the tropics, we see this 4-fold difference in the maximum cloud radiative heating. And we can kind of give a vertically stratified recipe for larger cloud radiative heating that involves more efficient heterogeneous ice nucleation at low altitudes, decreased conversion to snow at the middle altitudes, and these kinds of microphysical dynamic feedbacks that promote homogeneous nucleation at the uppermost altitudes. So then I want to transition to a second perspective here that has to do with source and sinks. So again, there's kind of a mathematical formulation of that perspective here, where we think about ice mass and number as being a function of sources and sinks that in turn depend on cloud parameters and cloud controlling factors. And to use this perspective, then we're again going to run limited area simulations. But now we're going to switch the domain and move to the North Atlantic. We're running our simulations again with the ICON model. In this case, they last over 14 days that correspond to the NODX field campaign in September and October 2016, and we're just going to use the default vertical resolution in this case. And we again sort of have model settings that we're going to play with. So the first is, again, this microphysics scheme, whether we're using a 1-moment scheme that just tracks the mass of ice in the cloud, or the 2-moment scheme that tracks both mass and number. In this case, we're going to change horizontal resolution from 80 kilometers down to 2.5 kilometers. So we have a range of horizontal resolutions that spans what we might use in a typical global climate model down to what we're using in the new generation of sort of storm resolving models. And in this set of simulations, then we're also going to look at convection. Explicit convection in the case of the 2.5 kilometer simulation, and for parameterized convection in the case of the more coarse resolution simulations. And then I want to do the same exercise with cloud-radiative heating profiles that we did over that Asian monsoon domain. So here we're looking first at the cloud-radiative heating profiles for reanalysis in the dashed and dotted lines, and again for a satellite climatology in the solid black. And so this problem of inconsistent baseline comes up again, right? We don't even have agreement between the reanalysis and the satellite product. So we don't have something consistent to which we want to compare. Now, if we go in and start to add our simulations, here you see the 80 kilometer resolution simulation profile in dark red. And we have daily standard deviation in the lighter shading and standard error in the darker shading. And then I'm going to sort of add in the simulations then with higher horizontal resolution. So here's 40 kilometers, 20, 10, and 5. And so you can sort of see as we move to higher vertical resolution, then we're reducing the cloud top cooling and the in-cloud heating down here. So we're reducing the dipole with higher higher horizontal resolution. So these were for the 1-moment simulation. Let's do the same activity for the 2-moment simulations. So we start with our 80 kilometer profile and add in 40, 20, 10, and 5. So the first thing to notice, right, is that qualitatively we have a somewhat different profile than in the 1-moment simulation. So we don't see that in-cloud heating between about 5 and 7 kilometers that we see in the 1-moment simulation. We just see the cooling over the depth from 5 to 15 kilometers here. But we do again see that as we move towards higher resolution, that the cooling, the cloud-radiative cooling here is reduced. So let's put these sets of profiles next to one another, and then also add in the 2.5 kilometer simulations in blue dashed and dotted lines. So we have 1 moment on the left and 2 moments on the right. And so what should kind of jump out at you is that for the 1-moment simulation, that 2.5 kilometer simulation kind of agrees with this trend of reducing the dipole at higher resolutions. At the 2-moment simulation, then things kind of go haywire and we get a completely different profile. So we have this large cloud-radiative heating peak that appears below about 9 kilometers, and we shift cloud top cooling up by about 2 kilometers. So we get a very different profile, turning off convective parameterization in combination with the 2-moment scheme. So again, the takeaway from kind of building these profiles up again is that we see a much stronger dependence on microphysics and convection schemes than on horizontal resolution in these simulations. And so again, we want to understand where these dependencies come from. And in this case, we started with macrophysical cloud variables. And we said, well, maybe these dependencies are due to differing occurrence of certain cloud types. Maybe if I turn on my convective parameterization, I produce less deep convection or more isolated cirrus. So to think about this question of occurrence frequency, then we use a cloud vertical class decomposition as in Oreopoulos et al. And you see that conceptualized here. So there are 3 layers, similar to the ISCCP, with low, middle, and high cloud. And then we look at cloud fraction in these 3 layers and classify grid cells as having isolated low cloud, isolated middle, continuous low middle cloud, and so on. So if we use this classification on our different simulations, what we find is that there's not a lot of difference in the occurrence frequency of different classes across the resolutions. So again, 80 kilometers is in this dark red, all the way down to our 2.5 kilometer simulations with explicit convection in the light blue. And so across resolutions, including the convection scheme in the 2.5 kilometer case, and we don't see large shifts in the occurrence frequency of different classes of cloud. So another macrophysical cloud variable that might be responsible is coverage, right? We might get different fractions of these cloud types. And so in looking at cloud fraction across these classes, we're going to focus on a subset of the classes now that are the ones that drive that upper tropospheric cloud radiative heating. So the classes that involve high clouds. So here are profiles of our cloud fraction across the different simulations, across the different resolutions, and with the convection scheme turned off. And we do see a slight increase in the amount of cloud that forms when we turn off the convective parameterization. If we decompose this into those 4 classes that involve high clouds, though, we still don't get a signal that's on par with what we saw in the cloud radiative heating profile. So maybe this plays a factor, producing slightly more cloud, but also in regard to resolution dependence, this doesn't seem to be explaining the whole story. So what changes much more in sync with the cloud radiative heating profile is the amount of condensate in the cloud, and in particular, the amount of frozen condensate ice within the cloud. So you can see in these cloud ice profiles that kind of smooth increase with resolution up to 5 kilometers, and then that dramatic change in the 2.5 kilometer simulations when we turn the convective parameterization off. So this very closely mirrors what we saw in the cloud radiative heating profile. And it's true not only averaged over all cloud classes, but also for those classes decomposed into the ones that involve high clouds. So we see it across the board, this kind of jump in the amount of cloud ice when we turn off convective parameterization. So we found our culprit. And the dependencies are due to differing ice condensate, but not really to differing liquid condensate. So we see a little bit of increase in the amount of liquid condensate from the coarsest resolution simulations, but again, it's nothing that's on par with what we saw in the cloud radiative heating profile. And so this is still work which is in preparation, but we're using this sort of sink source perspective to understand again why we see transition to higher amounts of cloud ice, particularly in the 2-moment scheme, and turning off the convective parameterization. And so the way that this works would be to look at the schemes and classify processes first as sources, so nucleation, growth, droplet freezing, riming, and sinks that include autoconversion, sublimation, sedimentation, and melting. And so we've looked at the liquid profile just now and seen that they're not strong changes in the liquid phase. And so we focus only on frozen phase processes. And then just sort of schematicizing this, we've already talked about the 1-moment and 2-moment nucleation and autoconversion in the 1-moment versus 2-moment scheme. And we saw nucleation is much weaker and autoconversion is much stronger. So we already have an imbalance in these sources and sinks. And I'll just note 2 other factors that we've identified in our analysis then that seem to be influential. So I said that these sources and sinks are a function of cloud parameters. And a particularly influential cloud parameter seems to be the initial mass of crystals, because that initial mass is going to drive things like growth and sedimentation and sublimation. And in particular, then in the 1 moment scheme, the initial mass of crystals is larger. And that means then that they'll grow faster and they'll sediment out more rapidly. And they tend to sediment out then to regions that are subsaturated, where they can then sublimate. And a final factor then that seems to be important in these simulations is the distribution of vertical velocities. So you can see that distribution here for the 2 moment schemes across the horizontal resolutions. And as you might expect, then as we move to higher resolutions, and then when we turn the convective parameterization off, we broaden that distribution of vertical velocities. So we get more extreme descent, but also more extreme ascent. And that extreme ascent will promote something like nucleation. So with that, I'll wrap up the second perspective of source sink budget and say again, in the mid-latitude simulations, we see large variability in the cloud radiative heating to the extent that it changes sign across different simulations. And then we can begin to understand that by looking at source and sink processes that involve cloud parameters and cloud controlling factors, and think about them sort of in this balance framework where we look at what's stronger and weaker. So I want to give one more perspective and then I'll wrap up. And that third perspective then is kind of a temporal one where we're going to think about cloud ice mass and number as a function of sources and sinks that are time dependent. And the motivation here was to constrain microphysical dynamic feedbacks. So let me explain what I mean by that. We've been looking at how cloud ice forms as a function of thermodynamic variables and flow field. Once that cloud ice forms, then it generates a cloud radiative heating, right? And that cloud radiative heating is proportional to the amount of condensate that we have in the cloud. We've seen that a couple times now. But it's also the case that once the ice generates a cloud radiative heating, then that cloud radiative heating can feed back onto the flow field, right? So radiative heating generates buoyancy locally within the parcel and can promote further ascent, right? And that further ascent will produce supersaturation, like I mentioned in the first part. And if we produce supersaturation, then we're feeding back onto nucleation, or we're further promoting nucleation. So we have this kind of positive feedback between ice formation and radiative heating. And what we'd like to do then is just look at the direct effect of ice formation on radiative heating and kind of cut off this feedback of the radiative heating onto the flow field. So we do that by constraining inputs to microphysics schemes along trajectories. You can think of this as a variant of something that's called microphysical piggybacking, if you're familiar. We call what we're doing with the trajectories Lagrangian piggybacking. So the idea is that within a storm resolving model, we're going to generate trajectories, and those trajectories then track the flow field over time, as well as the pressure. And then in the online simulation, that flow field and pressure are used as inputs to the online microphysics scheme that produces our mass and number in the cloud. But we can also take those trajectories and use them to drive an offline scheme. So we're using the same set of inputs to drive two separate microphysics schemes. And so in the work that I'm going to show you, the offline microphysics scheme that we're using is a 2-moment scheme called clams ice that's been developed at the research center in Jülich. So for this study, we're going to return to that tropical domain, to the Asian monsoon region, and you see our trajectories here. So they're initiated in the eastern part of the subdomain over the Sichuan Basin, and then they propagate over about 50 hours westward over India. And they're colored then by the altitude from at which they're located. And we're going to run a couple of these trajectory simulations. And so for each one, we have about 30,000 trajectories that we produce We run a total of 6 simulations. I said they propagate westward for about 50 hours, which corresponds to 8,000 time points. So in the end, we have a very robust sample. We have about 1.5 billion points along these trajectories that we're looking at. Then these 6 simulations, again, if we sort of think about this kind of switch idea, then the 6 simulations are either going to use that offline microphysics CLAMS ice or the online microphysics within the ICON model. And we're also going to use a temperature fluctuation parameterization that kind of mimics gravity waves, and we're going to turn those temperature fluctuations then either on or off. And again, then with microphysics, we're going to use a 1-moment or a 2-moment microphysics within ICON. So let me show you how distributions of cloud ice mass compare across these 6 different sets of trajectories. So we have the 2-moment distributions in blue and the 1-moment in orange. And then in the dashed lines, we have the ICON trajectories, and in the solid line, we have the CLAMS ice trajectories. And so if we use the median of these distributions as kind of our metric to compare them, then we see that even with these feedbacks constrained, right? So the microphysics that are being run with the same set of inputs, even with the feedbacks constrained, the median amount of cloud ice mass produced across the trajectories varies by a factor of 4.5, right? That means that the structural differences in the microphysics, 1-moment to 2-moment or ICON to CLAMS, are sufficient to generate this factor of 4 difference. And it's also maybe interesting to note that, again, using the median as our metric, that the 2-moment schemes in blue differ more from one another than the 1-moment schemes, right? So as we move towards these more sophisticated schemes, and there's also the potential that we increase this variability. I also show then probability distributions of the ice crystal number across the different trajectories. And again, with the feedbacks constrained, that median ice crystal number can vary by a factor of 6, right? And one other thing to note here is that when we use that temperature fluctuation parameterization that I mentioned, which mimics gravity waves, then we don't see a huge impact. You can see that, for example, looking at the different blue traces here, where 0T means the temperature fluctuation parameterization is off and 1T means it's on. So we see much bigger differences switching microphysics schemes than turning this temperature fluctuation parameterization on and off. So I'll show you one more analysis, I guess 2 more analyses that we do. We look at the distribution of cloud ice mass across temperatures for these different trajectories. And this distribution of cloud ice mass across temperatures is also qualitatively quite different. So in this CLAMS ice simulation up here in the upper left, we see a much broader range of cloud ice mass produced than, for example, in the ICON simulations over here. If we use CLAMS ice in a 2-moment formulation, then we get a much broader temperature distribution or ice formation over a much broader range of temperatures. So the final thing that we do then is to take these kinds of temperature distributions of the ice mass and use them to approximately scale the cloud-radiative heating from these trajectories, and cloud-radiative heating in this case in the long wave. So we assume an absorption cross-section and a lapse rate, and then from those temperature distributions of cloud ice mass, we do a fitting where we look at the temperature depth of non-negligible cloud ice mass, as well as the temperature dependence of cloud ice mass within that range. And if we do this kind of approximate scaling, then we get about a factor of 2. So even with the inputs to the microphysics schemes constrained, we can still get a fairly large range in the cloud-radiative heating. So with that, I will bring back up these 3 perspectives, 3 ways that we're sort of trying to think about understanding how cloud ice microphysics affects cloud radiative heating. We started with this vertical stratification idea that the cloud ice is a function of source and sinks that are temperature dependent. The second focuses more on the source sink dichotomy and the relative strength of source and sink processes. And this final perspective is then a temporal one, where we constrain the ability of the microphysics to feedback on the flow field. So this is 3 ways of kind of thinking about this question. And then I'll just bring up the overarching question again: how much does cloud ice microphysics contribute to cloud radiative heating variability? And the answer is quite a lot. So we've looked at it in different regions, right? We saw it's up to 4-fold if we're thinking about maximum values, 4-fold in the tropics, 5-fold in the mid-latitudes, and even 2-fold if we constrain microphysical dynamic feedbacks. So there's a very strong link here. And what should we kind of take away? How can we do better in constraining this simulated cloud radiative heating, and especially given that it has these strong implications for circulation? Well, I think a primary takeaway from our analyses is that capturing the thermodynamics, right, those inputs, or the cloud macrophysics, so something like cloud fraction or occurrence of different cloud classes, is not sufficient to constrain the cloud radiative heating variability. We really have to get the amount of condensate that's in the cloud correct. So we really have to get the cloud microphysics correct. And that involves a number of different things, correctly producing the distribution of vertical velocities, which will be helped, as we are transitioning towards these resolutions that explicitly resolve deep convection. It's also important to think about which species are radiatively active. We've seen multiple times that making snow radiatively inactive has a very strong influence on the cloud radiative heating profile. And this may be remedied in part by transitioning towards particle property schemes that don't differentiate, for example, between ice and snow. It's also important to include aerosol dependence in that heterogeneous nucleation efficiency. We can't make things solely a function of temperature because they're very poorly constrained only as a function of temperature. And a final comment I'll make then is the importance of this initial mass of ice crystals. So if I had to give you 4 tips to sort of constrain your cloud radiative heating profile, these would be those 4 tips. So that's all I have. Thank you very much for listening, and I'm happy to take any questions.
Okay, thank you very much, Sylvia, for that very interesting talk. So we have plenty of time for questions now. So feel free to either put a question in chat if you prefer, or also raise your hand and I'll be happy to ask you to unmute and ask your questions. So please, any questions or comments? Okay, well, I'll start with one question for you. Oh,
I
go
have
ahead.
one, Greg.
Okay, go ahead, Andy, please.
Yeah, what happens with cloud top inversion? And second, I wasn't quite clear on day-night variability.
Right. Well, let me address the second factor first. We haven't looked at things that are diurnally resolved, or that, everything is diurnally averaged here. We have not looked at differences, over the daily cycle. But that would also be an interesting factor. What was the first comment to cloud top inversion? I'm not sure what you mean by that.
Well, it seems as though you won't get uplift at cloud top if there's an inversion, which is often the case.
Right. Well, primarily for low clouds, right? And we're focused here more on high clouds. I'm sorry, I'm not sure I understand.
Yeah, often at cloud top, for example, with generating cells, there's an inversion at cloud top.
Okay.
And it seems like that would limit radiative effects.
Okay. Yeah, this is not a factor that we've looked at. We haven't, for example, stratified by temperature gradient at cloud top or anything like that. Yeah, that could be an interesting factor to look at also.
Okay, we also have a question online from Yongji Huang, asking about different microphysics schemes of different assumptions like size distributions, parameterizations of microphysical processes. So different schemes may have their own systematic biases. So he's asking how you make your conclusions more general that are not dependent on the particular two schemes that you used.
Okay, I see. Yeah, this is a difficult question, right? So even if I can sort of compare A and B and say, the initial mass in A is initial crystal mass in A is larger than B, and that implies this. You know, the microphysics scheme as a whole is a bunch of different pieces sort of talking to one another, and those pieces will be different in any scheme. The only answer that I have is that this is the best place to start, I think, by taking two schemes and at least trying to understand within these two schemes, you know, how do source and sinks and cloud parameters, cloud controlling factors compare between the two schemes. I think it's the best place to start. And then, yeah.
Okay, thank you. Any other questions?
Hi, I would have a small question.
Please go ahead.
Yeah, thank you for your talk. It was really interesting. I was wondering about, you showed how Calypso measurements and error results were really different in cloud radiative heating. Do you know why or where that comes from?
Yeah, that's a good question. I mean, there are microphysical assumptions that go into, especially into the ERA profile. The microphysics scheme that ERA uses is very simple. I think it's a one moment. I'm not sure about ERA 5, but certainly for ERA interim, I think it's a one moment scheme that's only temperature dependent. So those microphysical assumptions that are going into ERA, you know, as opposed to the CloudSat retrieval are going to be influential. Why exactly, for example, the CloudSat profile tends to be multimodal, whereas the ERA one tends to be unimodal. Why that, you know, specific details in that regard, I'm not entirely clear on.
Thank you.
Sylvia, though I'm co-author, I have a question.
Yeah, go ahead.
Yeah, so you showed us that it's quite a mess, but is there, let's say, some hope to, to get kind of a good answer and not only a huge variety? So I remember we talked about some comparisons with observations. Do you think, is that possible or not? So to have at least an idea which is the right direction.
Right. Well, I mean, I will say, I think these 4 kind of bullet points at the end are supposed to be sort of, at least for model development, maybe sort of directions in which we might go to minimize the variability in these radiative heating profiles. Thereafter, in terms of using observations, I think, you know, the only comparison to observations I've done here is to reanalysis, which is sort of a pseudo observation, and satellite data, maybe then also using in situ observations is kind of a good next step. I mean, it makes sense, right? You're looking at the radiative effect of clouds within the atmosphere, so you should use within atmosphere observations to look at.
I remember that we talked about comparison with aircraft observations, but maybe if you talk to Audron, maybe data and ice product would also something to use, because there you have a much broader view than you have with the in situ observation. Or you might do both if you have cases where you have both. Could be.
Right, yeah, it's always this trade-off between good coverage, which data might give us, and sort of reduced microphysical uncertainties, which in situ data might give us. So.
Just as an idea so that you don't get bored at work.
Thank you.
We also have another question online from Irene Bartoloma Garcia. Thank you very much for this interesting talk. I was wondering if you could explain a little more about the explicit convection in the model. How is it described?
Yeah, so that's, I guess, the second section. At 2.5 kilometer resolution, we had two different simulations, one in which we just let convection, we turn off all the convection schemes, and a second in which we turn on a shallow convection scheme. So we let deep convection be explicitly represented, and shallow convection is parameterized by the TIDCA. I think I'm pronouncing that right, the TIDCA scheme. For the simulations with coarser than 2.5 kilometer resolution, then we use convection schemes for both the deep and the shallow convection. I hope that explained.
Okay, thank you very much. I think, she sends her thanks. Any final questions? Okay, well, I think we'll make two. I'll make one concluding announcement first, then I'll hand it to Martina, who will make another concluding announcement. I'd like to remind everybody that at the YAMAS IUGG meeting 2023, July 23 in Berlin, there's quite a few different sessions that ICCP is sponsoring. So it'd be a very good venue to present your latest results. So please consider submitting an abstract to the meeting in Berlin in July. And then Martina, you have a couple of announcements as well, or at least one announcement.
I was muted. Yeah, the first announcement is that together with Greg and also Peter Spichlinger, so we organize a workshop after the IUGG meeting at the University of Mainz. I hope that all of you got the invitation. So today is the deadline for registering simply by writing an email to me, and we have. So this workshop is restricted to 75 people, but we still have some places left. So if you are interested, please let me know. And the second thing I want to announce is, can you see my screen already?
Yes, we can.
Yeah, and so this is the program of the ICCP Journal Club for the next month. So our next talk is already in 2 weeks, because we didn't want to bother you with clouds around Christmas and New Year's Eve. So we have it already in 2 weeks, and the talk is from a co-worker of Greg, Andrew. I don't know how to pronounce the last
DeZambo.
DeZambo, and the talk is on quantifying uncertainty in ice particle fall velocity relationships. And this is from in situ observations. And I hope that many of you will join, and others too. And yeah, that's all I like to mention here. And the very last thing, I'm sorry for Audron, there's no goal for France until now. So they play with Tunisia. Yeah, but no goal. That's it. Thank you.
Okay, well, thank everybody very much for attending, and just remind you that all of these talks will ultimately be available online. So if you missed something today, you will have a chance to see it a later time. So thanks everybody for attending, and we look forward to seeing everybody again in 2 weeks' time.
Bye, Sylvia. Thank you again.